This is my lab 3 on black holes for physics 2211. So this lab will again use second law, which states that an object in motion will remain in motion unless it is influenced by a force. This force is F net, which is equal to mass times acceleration, and we will also be using the momentum principle to derive the position and velocity update formulas that we will use later. This lab introduces the universal gravitation, which is a non-constant force between two attracting masses. And then we will also introduce parallel and perpendicular forces that makes up F net. So the purpose of this lab for part 1, we're going to find the mass of black hole computationally and simulate planet's motion with the net forces working on it. Then for part 2, we have a spaceship and we want to find the initial velocity so that it can escape this system with the black hole in it and make the ship and planet move in their respective trajectories. This lab is going to help us observe Newton's second law and the momentum principle, as well as the effect, universal gravitation, and work with parallel and perpendicular forces. So for part 1, the system was the black hole, the surroundings was the stars, and for the initial conditions, I found the initial and final momentum vectors of the stars, and I also made delta t to be the amount of seconds in a day. So I used all of that information to find the mass of the black hole when calculating F net perpendicular. It's important to note that F net is equal to the sum of the components. So F net is just perpendicular, is equal to the net force minus parallel. So the results of part 1. You can see here, yeah. And you can see that I calculated the average mass of the to 7.57 times 10 to the power 33. And so what does that mean? It means that the net force is the same as the rate of change in momentum, and each parallel and perpendicular component aligns with the other. This is all stated in the momentum principle. And so this is why we could make assumptions about the net force based on the object motion. So then for part 2, the motion of the spaceship. So the system is the spaceship, and the surroundings are the black hole in the planet and the planet. And the only initial condition change was the mass of the black hole, which I changed to the mass that I calculated in the last part. And then I found the distance vectors needed for the universal gravitational force formula, and used the gravitational equation that doesn't use the RAB vector, and that's why the magnitude is raised to the 3rd power, and they multiplied the distance vector, and I found the net forces on the planet and the ship. Then I used the velocity and position update formulas to find the ship's position, and basically this is my picture here. It went very close to the black hole, but it still managed to escape the system. And for the components of the ship, speed x and speed y, you just had to guess and check. I found that 4.68 and 2 were the scales that worked best for me. So For the what if question, the initial velocity would have been, so what if the initial velocity would have been lower, x, and slightly higher for y than what it was? Because the original velocity, the larger x component allowed the spaceship to escape the gravitational pull. So once again, I was just guessing and checking for this one. So I just used negative 0.4 as a scale of x, and then one was just y, and that's how I made it start. Your bit. Possible sources of error. Could not be, I might not have been running the program for long enough to calculate the average mass of black hole. Obviously, the longer you do it, the more accurate it's going to be. And another source of error would be guessing values for the initial velocity. So overall, I calculated the mass of the black hole and found the initial velocity needed for a spaceship to avoid crashing. And we used Newton's second law in universal gravitation, then observed the similarities and differences between momentum and force. Thank you for listening to my lab.